So the focus here is going to be on the curve sketching handout, which I asked you guys to print. It's on the class webpage. You scroll down to the document section. And so I also added the examples that we did that I wrote on the board last time for extra practice. We're not going to do all of the examples. I just want to get through a few of them. Today, I think we'll get through one of the more complicated ones as well as asymptotes, and maybe we might do some more next time as well. So let's actually just get into it. So let's move on to the topic of curve sketching. And remember that there's a handout for this. First, let's talk about something called asymptotes. So pretty much everything else we'd need for this topic we've covered before, except asymptotes. You never really spoke about those specifically. So let's talk a little bit about what these guys are and how we are going to find them. So, asymptotes. So, for a graph, an asymptote is a curve, a graph approaches as the x or the y coordinate approaches infinity, positive or negative. So as one coordinate is getting larger and larger and larger, either the x or y coordinate, if there is some other curve that your function tends to approach, this we call an asymptote. So for example, some common examples, you look at the tan inverse function. Asymptotes would be the horizontal line y equals pi over 2, as well as the horizontal line y equals minus pi over 2. So we know our graph behaves like that. So now you would notice, as the x coordinate is approaching infinity, the graph is approaching the curve y equals pi over 2. As your x coordinate is approaching negative infinity, your graph is approaching the curve y equals minus pi over 2. Or we can look at something like y equals, say, 1 over x minus 1. So notice at 1, we have division by 0, so we can't actually be there. So the graph is just a shifted 1 over x graph. Now this graph will also have asymptotes. There are two kinds. There's a horizontal one. You will notice that as the x coordinate is approaching negative infinity, the graph is getting closer to the line y equals 0. As it is approaching positive infinity, the graph is approaching 0 as well. However, there is a situation where your graph is approaching this curve as your y coordinate is going off to infinity. And so this thing here, this line, the line x equals 1, would be called an asymptote of that graph. You can even look at log graphs, for example. They're asymptotic, you would say, to the y axis. So your y coordinate is going off to negative infinity as you're getting closer to this point. So whenever a curve has this behavior, we say it's approaching an asymptote. Now you can have asymptotes of various kinds. They don't have to be straight lines. However, we only care about two kinds of asymptotes, so I'm going to talk about those specifically. So we only care about two kinds, horizontal and vertical asymptotes. Not that these are the only important kinds, these are just the kinds that you tend to care about in a Calculus 1 class for what you want to be able to do. So horizontal and vertical asymptotes. And maybe I'll just give you an abbreviation here. So horizontal asymptotes, I'll call those HA, because I can't bother writing it down all the time. These guys I'll call VA. So let's deal with one at a time. It turns out that you can describe these guys in terms of limits. We're all experts on at this point. So let me just write these down. Whenever you're focusing on an HA. So this is just when asymptote is a horizontal line. So whenever your curve is approaching a horizontal straight line, we say you have a horizontal asymptote. For example, the arctan function had two horizontal asymptotes. The 1 over x minus 1 function had one horizontal asymptote, namely y equals 0 for that one. And so basically you want to know how to find these. To find them, compute two limits. You find the limit as x approaches infinity of f of x, and you find the limit as x approaches minus infinity of f of x. Now, back in the day, you didn't have the language of limits, but back in pre-calc class, this would be what you refer to as end behavior. So whenever you were talking about, oh, let's graph this thing, let's talk about the end behavior. What you really were doing, you were finding these two limits, but back in pre-calc, they couldn't really say that's what you were doing. So you would find those two limits. You find the infinite limits of the function. And here's how a horizontal asymptote arises if, right, so you might not have a horizontal asymptote, but if either of these give you a finite value. Say L, then y equals L is a horizontal asymptote for the graph. So you might compute these limits, you might get does not exist, or you might get positive or negative infinity as the answer. In these cases, there is no horizontal asymptote. Okay? A horizontal asymptote will occur if either of these limits gives you a constant value. So for example, let's say you find this limit and you get 2 is the answer. Y equals 2 is a horizontal asymptote. Okay? And that's it. That's how you find horizontal asymptotes. You find these two limits. Maybe one more thing I want to mention about horizontal asymptotes. In general, it is not strange for a function to cross its horizontal asymptote. So functions, there's nothing that says you can't cross these guys. So you might have, say, a horizontal asymptote, just this horizontal line here, and your graph could just do whatever, be jumping around this, cutting through it, but what the horizontal asymptote is, eventually you're going to approach that line, right? In any local region, you might be touching it, doesn't matter, but eventually if you tend towards that line, and it's a straight horizontal line, we call that a horizontal asymptote. It is not strange for you to cross this asymptote in one or several places, right? That shouldn't be a strange thing. When it comes to vertical asymptotes, we'll tend to think of it as being strange. You usually don't cross vertical asymptotes. But horizontal ones, there's nothing wrong with actually crossing them. So if you're ever not sure if you cross a horizontal asymptote, you can just check. Set your f of x value equal to the value of the horizontal asymptote and see if there's a solution to that equation. If there is, it means there's actually a point where the output of the function is exactly the y value of the asymptote, and you would cross the asymptote at that point. Let's talk about vertical asymptotes. These can also be spoken about in terms of limits. And we say x equals a, so that's the equation of a vertical line passing through the x-coordinate a, is a vertical asymptote if one of the following are true. If as you approach a from the right side of your function, the answer is infinite, or if you approach a from the left side of your function, the answer is infinite. Anytime one of these behaviors happen, you have a vertical asymptote. So you can look at, say, y equals 1 over x, and you can notice that the limit as x approaches 0 from the right of your function, in this case, is going to be positive infinity. The limit as x approaches 0 from the left of your function, in this case, is actually negative infinity. Both of these, either or both of these would conclude that x equals 0 is a vertical asymptote. Now, it's worth mentioning usually you won't have to think in terms of limits specifically for a vertical asymptote. And by we here, I mean Calc 1 people. In Calc 1 class, we usually only test you here in a very specific situation. That's all I'm going to test on. Functional functions. Okay. So that's ratio of polynomials. And for those, it turns out that there's an easy way to check where vertical asymptotes occur. And you don't really have to do a limit, but you do have to be able to simplify it. Just tell you how that works here for rational functions. X equals a is a vertical asymptote if this x value denominator 0. And there is nothing to cancel this 0 factor. So, for example, so the prime candidates for the vertical asymptote will be the x values that make the denominator 0. But ever so often, they actually won't give you a vertical asymptote because you can kind of cancel them away. So again, so example, if I'm looking at y equals 1 over x, I can immediately see that setting x equals 0 gives a 0 denominator. And then I realize that nothing's present that can cancel that x in the denominator. Right? So I can't simplify this to cancel the x so that I don't divide by 0. That means x equals 0 is a vertical asymptote. Right? X equals 0 makes the denominator 0, and there's no way you can kind of stop that. Conversely, if you consider this function, that is a different situation. You would realize here, oh, x equals 1 makes the denominator 0. But you would also notice that the function can be written like this, and you can kind of cancel away that problem. Now, what that means is that x equals 1 is not a vertical asymptote. Now, the function still doesn't exist when x equals 1. What happens when it cancels? What is the feature that you tend to see? It's a hole. There would be a hole at x equals 1 as opposed to a vertical asymptote. Basically, this is saying, here's some fraction. Now, as long as we're not at 1, we can just cancel away the denominator, and so our function is going to behave like y equals x plus 1. So that's pretty much a straight line. Right? However, since we're dividing by x minus 1, a division by 0 is created at the location where 1 would happen, and that happens to induce what we call a hole. So at that point, we can't actually compute the output of the function, but anywhere else, the function behaves like a straight line. Right? So whenever you can cancel away the problem in the denominator, it causes a hole as opposed to an asymptote. Asymptotes occur when you can't actually cancel. So the quick way to figure out if a rational function has a vertical asymptote somewhere, find where the denominator is 0, make sure nothing in the numerator cancels that thing. And that's pretty much it. Okay? If that thing can be cancelled, it means that you have a hole, not an asymptote. Now, unlike horizontal asymptotes, for us it's quite strange for a function to cross its vertical asymptote. For us, meaning Calc 1 people, there are functions that do this, but they're very strange. For us, it's very strange to cross your vertical asymptote. In fact, rational functions never cross their vertical asymptotes. So if I ask you to graph a rational function, you find a vertical asymptote and you draw a curve across that line, so it's not that it's strange in general. For the function that we deal with in Calc 1, it's kind of strange, right? Because usually a vertical asymptote occurs when a division by 0 occurs, and you can't have a function having meaning at a division by 0. So for us, for rational functions, the vertical asymptotes occur when the denominator is 0, so you can't touch that vertical line. So that's one way in which they're particularly distinct from horizontal asymptotes. Horizontal asymptotes really only take effect when you're far to the right or far to the left, and your x is going to infinity. But in the meantime, in the middle, your function can do whatever it wants, essentially. For vertical asymptotes, usually a vertical asymptote arises when a bad situation like division by 0 is occurring, or your function just won't make sense. So you can even think about the log function. It just doesn't make sense to have the log of 0. So your function is just going to avoid that line. So vertical asymptotes really have a lot of issues with them. There are some functions who might cross their vertical asymptotes, but they can do that at most one time. And that's because if you cross it twice, you're not a function anymore. So vertical asymptotes are very restrictive. Okay, and I think that's pretty much all I need to know about asymptotes, because we only care about 2 types. And I mentioned them here in the handout. So last time we were talking about, and these were the examples that I listed on the board last time. I'm actually kind of going to want to skip over them and talk about these down here. But last time we talked about what a second derivative does, what a first derivative does, what the original function tells us, and all that stuff. And we were going to illustrate with these. But in general, the way you would illustrate your knowledge of these ideas in a Calc 1 class would be with curve sketching. Now, curve sketching isn't something you'll be doing a lot of actually in practice in the real world, because we have machines and calculators that are pretty good at sketching curves better than a human, better and faster than a human being would be able to do it. However, it's hard to test you on the nuances of whether you understand what a derivative means, what it tells you, how it causes a function to behave. And so pretty much the topic of curve sketching is meant to test your knowledge there. So that's why it's there. As well as there are sometimes you'll see in your future classes where doing a quick sketch of something can help you figure a problem out, and you won't always have like a computer right beside you to do that. So you should be able to sketch several things fairly quickly, and this can help with that as well. Although pretty much your knowledge from pre-calc could have helped you do that. But we're going to sketch things in a lot of detail here to really show that we understand what concavity means, how we would find one, etc., etc. And so that leads us to curve sketching. So curve sketching, like a lot of the other related rates and optimization and all that stuff, there's a sequence of steps that you kind of always follow, right? So there's an algorithm to go through for curve sketching, and I listed that in the handout. I also talk about some common mistakes and things you want to look out for, and then we go through examples. So the first thing, of course, is to observe the domain of your function. Remember last time we were in a situation where we did the first derivative test and it was like something was increasing and then something was decreasing, and then I asked you, was this point a maximum? And the answer was no, because that point wasn't in the domain. Right? So you always want to know your domain. What x values are you allowed to actually plug in? Where is your function allowed to exist? The next thing you're going to want to find is the intercepts. Then you're going to want to find the asymptotes, and by that I mean the vertical and horizontal ones. Then you're going to want to find the intervals of increase, decrease, and maximums and minimums. And we learned last time that the first derivative is the guy that's going to tell you about that. Then you're going to want to find the intervals of concavity and inflection points. The second derivative is going to tell you about that. And so step 5 and 6 would use the first derivative test and the concavity test respectively, 4 and 5. And then step 6, the final question, is to actually sketch a graph of the function that has all the features that you found. Now, in terms of what you can be expected to be tested on. Okay, so these were the problems we were going through last time. It was kind of to illustrate the ideas and the concepts. I'm probably never going to ask you to sketch functions that look like this in general, like a regular polynomial. It's very pre-calcish. More likely, on a quiz or a test, I'm going to ask you about a problem that looks like in the second set of examples. So I kind of want to jump ahead and do one of those examples. And depending on how much you guys understand, we can actually do some more examples afterwards. So normally, a problem in a test or a quiz will look like this. Okay? So basically it's going to say, okay, consider this given function. The formula for the first derivative and second derivative are given and need not be verified. Okay? So here you'll notice I gave you a function and I gave you its first and second derivative. Okay? So by the time you get to this point, earlier in that test, or I would have usually have tested your ability to find derivatives already. So I'm not going to test that with a curve sketching. I'm just going to say, here are the derivatives. You don't have to find them, right? I just want to know, do you know what they mean? Do you know how to use them? That's what I care about with a curve sketching problem, okay? So typically I'm going to tell you a function. I'm also going to tell you its first and second derivative. And then I'm going to ask you to find certain things. So it's going to say, okay, given this information, find the intercepts, asymptotes, relative extrema, intervals of increase, decrease, and concavity inflections, and use that information to sketch the graph. Okay? And I might actually specifically ask you to find the domain as well. But that's basically going to be what you can expect a problem to be like. And so, yeah, probably next week's quiz that'll probably be it. I'm just gonna ask you this one question. Say, okay, here's a function, it's two derivatives. Sketch it, right? In order for you to do that, you'd have to find concavities and intervals of increase and all that stuff that I've been talking about over this past week. You'd have to be able to find all that stuff in order to sketch the picture anyway. So I just say, just sketch it. I can just give you a question like that and it'll test your knowledge on all these things. So pretty much want to go through one of these. Maybe we'll go through part A for now. And so you can see how these ideas are applied in practice. So on the handout, we're in the section more examples, which those are, exams and quizzes. That's the examples that I'm going to do. So at this point, I'm not going to test you on your ability to find a derivative. I'm going to assume you're an expert at that, so I'm just going to give them to you. Let's see if you know how to use them. So let's do part A, where I told you, okay, here's a function, x squared over x squared minus 4. Here is its derivative. It is minus 8x over x squared minus 4 all squared. Here is its second derivative. It is 8 times 3x squared plus 4 all over x squared minus 4. So don't waste time actually checking, are these correct? Just assume it's correct. So now I want you to find all the features that we've been talking about over the past week, and the asymptotes which I just spoke about a few minutes ago, and then you're going to draw a picture. So let's actually see what the graph of this thing would look like. So I didn't mention it here, but I probably would ask you to find it specifically on like a test or a quiz. Let's talk about the domain. Okay, so here's our function. Well, here's a bunch of functions. Where do we look for the domain? What is the domain here? What is the domain of this function? Alright.
Is it plus or minus 2? Oh wait, no.
No. Who was the other? Diego?
Would it be all real numbers except negative 2 and 2?
Yes, all numbers except plus or minus 2. Plus or minus 2 would cause a division by 0, so we avoid those. Anything else works. So that's minus infinity to minus 2, avoid minus 2, avoid 2, but everyone else works. So that's the domain. Right? So we know domains for rational functions, set the denominator equal to 0, solve for x. Those will not be the domain. 2, we want to find the intercepts. So let's start with the x-intercepts. How do you find x-intercepts? Set y equals 0, solve for x. So you set y equals 0, and you would get 0 is equal to x squared over x squared minus 4. This means that your x would have to be 0. That's your x-intercept. And for y-intercept, of course, you do the opposite. You set x equals 0. You would end up with y equals 0 over minus 4. So that's your y-intercept. So this graph intercepts at the origin. It intercepts when your x and y are 0. So here's, speaking of the rookie mistakes, I want to, at this point you should notice there's only one x-intercept, right? That'll be important later. Right? Namely the origin. There's only one time it crosses the x and y intercept, and namely it's going to be the origin. So we move on to the next section. We're going to find asymptotes. Let's start with horizontal. How do you find the horizontal? Well, you're going to find the infinite limits. Limit as x approaches infinity of your function, and limit as x approaches negative infinity of your function. What's the first one? Yeah?
1.
It's 1. Highest powers on the top and bottom are the same, and we're taking an infinite limit, so it goes to the ratio of the leading coefficients. This will also be 1. This is not true in general, it's true for rational functions. Both would be the same answer, so you could find 1 if you want. But that's only true for rational functions. If you look at the arctangent function, you would realize that that's not true in general. But for rational functions, you find one, you've automatically found the other. Right? Because there's only 3 situations for infinite limits of rational functions. It's either 0 if the highest power is on the denominator, it's plus or minus infinity if the highest power is on the numerator, and that wouldn't give you a horizontal asymptote anyway. And if the highest power is on the top and the bottom, you take the ratio of the coefficients. In this case, it was that case, the latter case, and that gives you 1. Now you want to find the vertical asymptotes. So, as I said, for vertical asymptotes, these will occur when the denominator is equal to 0. And you have to check, is there anything in the numerator that could potentially cancel that and stop that from happening? The answer is no. So that's your vertical asymptotes. And here, this means that y equals 1 is your horizontal asymptote. The fourth thing we want to find. Intervals of increasing, decreasing, locations of maximums, minimums. For this, we use the first derivative. Every time we want information like that, we will always use the first derivative. So the question asks us to find the extrema and the intervals of increasing and decreasing, so we're going to look at the derivative. So what we need is the critical points. What are the critical points here? Or critical numbers. Yeah?
-2 and 2.
Sure. Anything else?
0.
Also 0. There are 3 critical points. 0 and 2 and minus 2. Okay? Remember, critical points occur where the derivative is 0 or undefined. Set this equal to 0 gives you x is 0 because x is in the numerator. Set it undefined, meaning the denominator is 0. That's going to be plus or minus 2. So you end up with these 3 values, which you are now going to test in the first derivative because you're looking for this. So here I have minus 2, 0, plus 2. And we're going to do the first derivative test. So I pick a random number. And then I'm going to test these. Now, remember what we care about here. We care about where the derivative is positive or negative. I don't care about particular values. So, ever so often, we have a function that is very convenient to work with. You will notice here that the denominator is a square, which means as long as it's not 0, it's always going to be positive. So in other words, I can ignore the denominator. I only care about the numerator. So now what I'm going to do is I'm going to plug these numbers into the numerator and see what sign I get. If I plug in a minus 3, minus 8 times minus 3 will give me a positive number. I don't care what number, I just care that it's positive. Plug in a minus 1, I'll get a positive number. Plug in a positive 1, I would get a negative number. Plug in a positive 3, I would get a negative number. I only care about the signs. What does positive mean here?
Increasing.
Increasing. Means the graph is going up as you move from left to right. Similarly, negative means you're moving down as you move from left to right. So those are the intervals of increasing and decreasing. Are there any extrema? Any maximums or minimums here? Or any candidates for maximums? Yep.
0.
So 0, notice at 0, you're increasing, then you're decreasing. Let's double check that we're not being faked out like we were last time. We look at the domain. Oh, 0 works. 0 is actually a coordinate, so this is a maximum. Right? The only bad points are these two. So if anything that looks like a max or min happened here, we just ignore it. It's nothing. Right? But 0 is completely fine. It's in the domain. So if you're increasing on the left and you're decreasing on the right, you have to hit a maximum here. Now, what if I wanted to find the location of the maximum? How would I do that? Find the actual coordinate. Yeah?
Plug the x value back into the original function.
You would, if you're looking for a location, you go back to the original function. So if I actually wanted to find the specific location of this maximum, I would actually plug 0 into the original function. Notice that the output here would be 0. So now I can summarize that and answer the problem, which I'm going to write here as increasing, decreasing, max, min. We are increasing on negative infinity to negative 2 and negative 2 to 0. We are decreasing on 0 to 2 and 2 to infinity. We have a maximum located at the origin, 0, 0. Minimum, we have none. So that is the answer to that section of the question. Also notice that these guys, the notation looks similar here, but notice these are intervals, while these are coordinates. Okay, so that's where I'm increasing, where I'm decreasing, and where I hit maximums or minimums. There is no minimum of this function, but there is a local maximum at 0, 0. So we found the domain, the intercepts, the asymptotes, where we're increasing, decreasing, where the local extrema are. The next thing we want to talk about is concavity and inflections. And of course, if we want to talk about concavity and inflections, the second derivative is who we want to talk about. We're going to look at f double prime, which is so we're going to look at its critical points. What are the critical points of this function? So we set it equal to 0 or undefined. It's clearly undefined at -2 and 2, but it's never 0, right? A fraction is only 0 if the numerator is 0, and you will notice that this numerator is always positive. Okay. So you notice that this numerator is always either 32 or larger, so it's never going to be, so those are the only two critical points. And again, we're going to test this on the number line. The difference is we're testing this in the second derivative because we're looking for concavity and inflections. So again, pick some random numbers. And now we are going to Again, let's look at our function. Remember, we don't care about the value, we care about the signs. So we can actually reduce the workload by just paying attention to things that won't contribute to the sign. Since the numerator is always going to be positive, I can essentially just ignore it. And let's just worry about the denominator. Right? That's not always the case, but in this case, that actually works. So if I plug in a -3 here, square that, I get 9, subtract 4, I get a positive number. Notice that if I had plugged in a +3, exactly the same thing would have happened. If I plug in a 0, I get 0 squared minus 4, that is a negative number. So now I tested that. What does positive mean in this case? Concave up like a cup. Negative, down like a frown. Positive, up like a cup. So this has nothing to do with increasing and decreasing, it's talking about the shape. Do we have any inflection points here? Well, we switched from a concave up to concave down, so does that mean this is an inflection? No, because it's not in the domain. If it was in the domain, it would be an inflection, but it's not. So we have no inflections here, and it's because plus or minus 2 is not in the domain. So that's why step 1. Step 1 really comes into play when you're trying to figure out whether or not a certain point has a certain behavior. If the point doesn't exist, it doesn't have that behavior. It's not in the domain. So naively looking at this, you might look at -2 and 2 as inflection points, but remembering that they're not in the domain means they can't. They're nothing. They're not actually on the graph. So then I can summarize that information. Talk about the intervals of concavity. Where is it concave up? Where is it concave down? Where are there inflection points? So I can see here I'm concave up, -infinity to -2, unit 2 to infinity. I am concave down between -2 and 2. Inflection points, I have none. Is that part of the question? And that's the last set of things we have to find. So now we are up to the graph. We found the domain, the intercepts, the asymptotes, where it's increasing, decreasing, where max and mins happen. Now we just found where it's concave up, concave down, and if there are inflection points. We have enough information to sketch the graph. So let's actually just do that. Now, what I like to do is all this information that I've just computed, I like to put that on the graph itself, just like draw a little skeleton before I actually do the graph. So I'm kind of going to show you what I like to do here. This is my x and y axis. Normally what I like to do first is plot coordinates. Right, so here I'm going to put in the intercepts. I'm going to put in the, if there are any max and mins. If there are any inflection points, I'll put those coordinates in. So far, we actually only have one coordinate to worry about. That is quite literally the origin. This was the x and y intercept, and it was also a maximum. There was no other x and y intercept. There was no other max and min. There was no inflection points. There was no other coordinate that was important to me. That's the only important coordinate, so there's that one coordinate. Okay. The second thing I would put in are the asymptotes. So we found that there was a horizontal asymptote at 1. So at 1, I would actually put in a horizontal line. I would draw it, you draw it as a broken line because it's not actually a part of the graph, it's just helping you figure out what the graph needs to look like. I also discovered that we have vertical asymptotes at positive and negative 2 on the x. So I put in the important coordinates. The next thing I put in are the asymptotes. Draw these as broken lines because they're not officially a part of the graph. They're just kind of guiding us as to what lines the graph needs to avoid, what lines should it be going towards, etc. And then I actually like to chart the intervals of increasing, decreasing, and concavity. So here's how I like to do it. So way to the bottom of the graph, again, this is not a part of the picture, I'm going to start putting in the intervals. So I might say, okay, we saw last time that it was increasing from negative infinity up to -2. So I'll just write a little thing here. So from this point going back, it's increasing, and I'll actually literally write that in. I also know it was increasing from -2 to 0, so that's increasing, I'll write that in. We realized it was decreasing from here to here, so I'll write that in, DEC, decreasing. And from here onwards, it is again decreasing. Right? So I write that in as an interval. There's a length that it will have this behavior for. Now when it came to concavity. So I know it's concave up here and here. So to the left of -2 and to the right of 2, we're concave up. So I'm going to write in here, okay, from that point all the way back, it's concave up. And from this point all the way forward, it is concave up. Between -2 and 2, it is concave down. So that means between here and here, it is concave down. And there are no inflection points to plot. So pretty much I went through and whatever I computed in those first 5 steps, I put all that information on the graph, right? So I don't have to be going back and forth and looking for numbers because you'll make errors doing that. Especially if like the things on the other side of the page and you're doing this and trying to sketch, you don't want to end up with that script. So I put all the information on the graph, on the axes. So now I'm just going to sketch a graph that has this behavior. So let's start with the middle region because that one's easier because I actually know a specific coordinate that works there. This has to be a maximum, so we have to be increasing towards it and then decreasing after it. So I know the graph is going up, it'll hit that point, then it'll start going down. Now I'm going to worry about how are you shaped while you're doing this? Well, it should be concave down, down like a frown. So in this region it tells me I'm increasing concave down. Right? So I'm increasing, I'm going up as I move from left to right, but I'm shaped like a frowny face. In this region, I am decreasing concave down. So I'm still shaped like a frowny face, but now I'm falling as I move from left to right. This is a vertical asymptote. Division by 0 happens there. My function cannot touch those lines. It will simply approach those lines. So that's what the middle of this graph looks like. Okay, so now let's worry about what does it look like in these regions here. Now, you could start to plug in random points here to see where your graph should be located, but you can also start to just think about it, and that'll probably be quicker. Think about it, what do you mean? Okay, start to ask yourself, should the graph be down here, for example? Okay, so suppose my graph is down here, and it has to be increasing, right? So my graph would do something like this, right? It can't pass that pink line, so it'll keep going up like that. Why would that be a problem? Yeah?
Because 0, 0 is the max.
No. 0, 0 is a local max. So if you're far from 0, that's not the problem.
X-intercept?
The x-intercept would be the problem. Earlier we found the x-intercept, we found there's only 1. If I started here and increased, I would have created another x-intercept. So the graph definitely cannot be down here. Okay, could it be up here, right? Between the x-axis and the asymptote. So then you're like, okay, well if I'm here and I'm increasing, I would cross the horizontal asymptote. Now in general that's not a problem, so you might just actually check, is that possible? Do I actually cross the horizontal asymptote anywhere? So now you might ask yourself, cross the HA? I don't know. I know I'm definitely not crossing the pink lines, but I might be able to cross the vertical lines. So how you realize that, you would ask, does f of x equal the value 1 at any point? Right? Is the output of my function on this line? Now your function is x squared over x squared minus 4. That would mean that your x squared is equal to x squared minus 4 by multiplying, cross multiplying. I can subtract x squared from both sides. That would mean your 0 is equal to minus 4, which is absurd. So the answer is no, I do not cross the horizontal asymptote, which means my graph cannot be here. It has to be up here. Right? So I can literally go through each region and ask myself the question, could I be here? No, because it would violate step 2. Could I be here? No, it'll violate that. I must be over here. Otherwise, you could have just plugged in a random number like minus 3. You'll realize that you're always getting y values that are above 1. So there are a couple ways to do that. But we know our graph is over here. I know it's moving up as I go from left to right. I know that's an asymptote. So that has to be the first part. It's going up. It's increasing. And it has to increase looking like a smiley face because it's concave up in this region. So I'm increasing concave up, and this behavior will continue. So that's the graph here. So it's going up. It doesn't touch the vertical asymptote. It also doesn't touch the horizontal asymptote. It's just approaching it. A similar logic will tell you the graph cannot be here and decreasing because that would create an x-intercept. Can't be here and decreasing because that would mean I cross the horizontal. The graph has to be above here. And so that's going to be the graph. It is falling as I move from left to right, decreasing. It is also concave up, shaped like a smiley face. And that's the picture. That's the picture of this graph. Yeah, there's a little hill in the middle, and then it goes off like that. So what I'd like you to do is try the other examples, those processes, and see if I can